Okay, let's continue on with the photoelectric effect. So the previous video was all the theory basically. Hope you understood it. If you need to, ask some questions or have a look at it again. But now we're going to do some examples of typical questions that you get from the photoelectric effect, and hopefully that will reinforce the theory and your understanding. So for sodium, the work function is 2.3 EVs. Now recognize that we can give the work function in joules or electron volts, and because we're dealing with atomic physics, sometimes it will be in electron volts. Now, does sodium exhibit the photoelectric effect for yellow light of wavelength 580 nanometers? So how are we going to solve this? Well, first step is we need to know the energy of the photon, and so we've got this photon. We use E of the photon equals HF, which equals HC on the wavelength. Convert the nanometers to meters by simply multiplying it by 10 to the minus 9. Speed of light 3 times by 10 to the 8, and Planck's constant. And so we work out that the energy of the photon is 3.4 times by 10 to the minus 19 joules. And of course we've given the work function as 2.3 EVs. We may as well convert this to EVs, electron volts, by dividing it by 1.6 times by 10 to the minus 19. That's the amount of energy, or the amount of coulombs, or the charge of electrons, probably the easiest way to say it. And so we work out that the energy of the photon is 2.1 EVs. If the work function is 2.3, this photon does not have enough energy to overcome the work function. Therefore, we wouldn't get the photoelectric effect. Now, we could have just as easily converted this to joules and then compared joules and got the same answer. So now here's another one. Ultraviolet light of wavelength 200 nanometers is incident on a clean silver surface. The work function for silver is 4.7 EVs. What is, now these are some typical questions that you might be asked. What is the kinetic energy of the fastest moving ejected electrons? The kinetic energy of the slowest moving electrons? The cutoff frequency for silver? The cutoff wavelength for silver? And the cutoff potential, or V-stop, for silver at 200 nanometers wavelength. So for A, we want the kinetic energy. So we've got this photon. We need to know how much energy the photon is. So we do the same thing again, and we work it out to be 9.9 by 10 to the minus 19 joules. We convert that to electron volts, 6.2 electron volts. Therefore, the photon has enough energy to overcome the work function, and so the kinetic energy will be the energy of the photon minus the work function. So you can work in EVs as long as you're consistent, or you can work in joules. Most often I get students to work in joules simply because that's a unit we're fairly familiar with, but you don't have to. So here we've got the photon's energy is 6.2, work function is 4.7, so the kinetic energy is going to be 1.5 EVs, and we could convert that to joules if necessary. Recognizing that that's how we convert 1 EV to joules. Next one, B, the kinetic energy of the slowest moving. The slowest moving electrons are those that only just escape the surface. Remember back to the theory, we had one only just reaching the surface, so their kinetic energy will be 0, and the only way we would notice those is if they found themselves in an electric field that pushed them to the collector plate. Now C, the cutoff frequency for silver. If that's the work function, we got HF equals the work function. HE, we convert the electron volts to joules, because E equals HF needs to be in joules, and because frequency is a standard unit, and so we then go divide it by moving Planck's constant across, and we get a frequency of 1.13 times by 10 to the 15 Hertz. Okay, let's have a look at D, the cutoff wavelength for silver. And so what we know now is we can actually use the equation E equals HF, and then we take that and make it into HC on the wavelength. Okay, and if we rearrange this, because we're after the wavelength, we get wavelength equals HC on E, where of course we're dealing with standard units, and so wavelength is going to be in meters. We need to have this in joules. And so what they've done here is they've taken the electron volts and they multiply it by the conversion factor for joules. And so you get your answer in wavelengths, and then they've moved the decimal place 1, 2, so that's 10 to the minus, so this is the same as writing 260 times by 10 to the minus 9, where that's a nano, and so 260 nanometers is the answer. Alright, let's get rid of that. Now, the cutoff potential VO for silver. Now, in part A, we learnt that the energy of the electrons is 1.5 EVs. That's the maximum kinetic energy that they have, and so the electric field to stop that requires 1.5 volts, and that's one of the advantages of working in electron volts for some parts of the photoelectric effect. Now, I'll be giving you this question that will probably be on your OneNote or in your workbook, so have a go at it. Very similar to the others, just test your understanding. This is all the working, and I'll also be giving you that. You can see that they get quite complicated and you have to be careful how you do them, but once you get an understanding of it, it does make sense. Now you should be able to do some questions as well in your workbook, which will be on the OneNote, and set 22 should also be able to be done. And in the next video we're actually going to look at X-rays. Bye.